Hi everyone and welcome to this new video. We continue with the power factor correction examples. This is our example number 2. In this example we have again an inductive load, shown here in a model, series combination of the resistor and the inductor. But this time the question in place is somewhat different than example 1. What is the question? There is a voltage given, Vs, which is shown here. The load, this complete load, will absorbs 3 kilowatts power with a power factor of 0.75 lagging. So there's a power factor of 0.75 lagging, and we would like to calculate the value of the capacitor, which is placed again here in parallel, the required value of the capacitor to raise the power factor to 0.9 lagging. Okay, let's start first making clear where we start. We start actually with 0.75 lagging, and we would like to go to 0.9 lagging. Let's first consider the situation without the capacitor. So what is actually the situation at the moment? So the power factor. So the power factor, which is given by PF. For this case, for power factor 1, so in this case, for the first case, power factor 1 is 0.75. This will be lagging, as shown here. Now, if you translate this to the phase, theta 1, that will be our cosine of the PF1, which will be lagging. So what we get is the following. If I substitute the value arc cosine of 0.75, I will have, again this will be lagging, this is very important, I will have a phase of approximately 41 degrees, so 41.4 degrees. There is also a real power given, so this is actually the true power, the dissipated power in this load without the capacitor. This is also our initial condition. Let's write that down also. The P, the power, the real power, is 3000 watts. Okay, that's also important to note. In this situation, the apparent power, so the first situation, is a factorial summation of the real power and the complex power. So that's the situation for in this case, and I will make this I will denote this by a vector. So this is actually a vector notation. So we have a real power factorial sum with the complex power, which is of course due to the inductor here. So what's this in the complex plane? How does it look like? If you sketch this in the complex plane for the real and the imaginary part, so the real part and the imaginary part. If you have the 3000 watts at the positive real axis, so this will be the P, and you will have the apparent power, that is the S1, will be here, and there is also a phase, which is this one, that's the theta 1. This will bring us actually to the value, pictorially, to the value of the Q1. So this is actually this. So as you can see, the vectorial sum of the P and the Q1 will make S1. And if you know the theta, which is now calculated, and if you know the P, which is also given, you can calculate S1. So let's write this down here. So what is the expression for this? The cosine of the theta 1 will be P divided by S1. So this will give us the following. The S1 will be P divided by cosine of theta 1. Now, since we know all those values, we can determine the S1. So S1 will be 3000 watts divided by cosine of 41.4 degrees. And this will give us 4000 volts amperes. So this is actually the unit for the apparent power. So it's not watts. Okay, that's actually the step one. After that, we can calculate the Q1. So let's do that also. So let's calculate Q1. How do we do that? It's actually again using the triangle here, actually trigonometry. You know that this is the Q1, the length of this part is also Q1, so you can use the formula using the S1. So let's do that. So sine of theta 1 will be Q1 divided by S1. And this will bring us to Q1. Q1 will be S1 times sine of theta 1, which is, of course, 4000 times sine of 41.4 degrees, which will be equal to 2645 volt amperes reactive. So note that the units for the reactive power will be VAR, and for the apparent power will be VA, and for the true power, the actual the dissipated power will be in watts. Okay, that's actually for this situation. Now let's consider the situation for what should happen after the capacitor is placed in parallel. So I will a little bit zoom out to make this clear. So I would like to describe the situation 2, which is actually for the power factor. So the power factor 2, which is PF2, which must be 0.9 lagging. I would like to increase my power factor from 0.75 to 0.9 lagging. Again, using the same formula for the theta, I will calculate the theta 2, exactly the same procedure. So what we get is the theta 2 will be equal to arc cosine of 0.9. So that will be 25.8 degrees. That's actually for the situation. Now let's sketch the new situation and the original situation in one graph, and I will make this a little bit bigger to illustrate the concept what we need to do. So let's move up a little bit and make this sketch here on the left side. So if I make the situation as follows, so real axis and imaginary axis. So we have the real axis and we have the imaginary axis. What is the original situation? The original situation is as follows. You have the real power, which is dissipating 3000 watts, that's the P. You have an original apparent power, which is S1, so it has also its own reactive power, so which is Q1. That's actually the situation for the first original circuit without the capacitor. Now with the capacitor in place, I would like to bring the theta from 41.4 to 25.8 degrees. That's actually the situation. So in the new one, I will make the drawing in black, or maybe in another color. I will make it in light blue. So if I want this is actually S2. Maybe better to choose another color because that's really hard to see. So I make it in yellow. So if I want this, there's a new one, and this phase, so new phase, so the new phase here will be theta 2. So what is theta 2? So let's calculate that. Theta 2 must be 25 degrees. Okay, and I would like to go to a new value for the reactive power, which is the Q2 here. So if I use again the trigonometry, because this is the phase I'm looking for, and this is the apparent power I'm looking for, and I need again 3000 watts, I can use again the trigonometry here to calculate the required value for the capacitor after this analysis. So what you can do first is determine what is actually the required decrease in the reactive power. So the decrease in the reactive power must be made by the capacitor. So the Q of C must reduce the Q1 to Q2. So you can already say QC is equal to Q1 minus Q2. That is actually the situation for this case. So if you determine Q2, the value of Q2, you know QC, and from QC you can determine the value of the capacitor. But first let's use this triangle and come up to the value of the S1, and from that we can move on and work through the Q2. Okay, let's move on. So what is S2? Let's make again the situation clear. So the cosine of theta 2 will be again P divided by S2. So this will bring us to S2 is equal to P divided by cosine of theta 2. Now if you now substitute again the component the values, or this is still 3000. So this is S2. And now cosine of 25.8 degrees, and this will give us the new value of the apparent power, which will be 3332 volt amperes. So that's actually the situation for this case. So I will make this blue. So this is for this case. Now the next part is the Q2. So let's determine Q2. Q2 has a relation with the apparent power again in this form. So the sine of theta 2 is equal to Q2 divided by S2. So that will bring us to Q2 is S2 times the sine of the theta 2. Now if you substitute the values which are given here, 3332 times the sine of 25.8 degrees will result in 1450 volt amperes reactive. So that's actually the situation here. So that's actually the new Q2. So if I want to reduce my value from 2645 to 1450, I need a reduction of, so what is it then? I need a QC, which is 2600. I will make it again clear that it's Q1 minus Q2. So this will be 2645 minus 1450, which will be 1195 volt amperes reactive. This is actually the required reactive power due to the capacitor only. So as we know, the capacitor, looking to the original circuit, the capacitor will be placed parallel to this load, which is also parallel to the voltage supply. Now comes the question, what is actually the value of the capacitor? Now, since you know the capacitor value can be determined from the capacitor reactance, the XC. So if you know this, assume this as an impedance or reactance, then you can know, if you know the volts across this element, and you know its reactance, then you can calculate the C, the value of the capacitor. I also know the Q, so I also know the reactive power. So using the reactive power formula in terms of the voltage across the capacitor and also in terms of the reactance C, I can determine the capacitor C. So let me write this down. So what we have is the following. If I know that the QC will be equal to the capacitor voltage, of course in RMS, which is required, squared divided by XC. But what is the VC RMS? VC RMS will be equal to the V supply RMS. But now comes the question, what is the V supply RMS? So V supply RMS, the question in place gave us the value of the supply voltage Vs, but this is an amplitude, so that's 25 volts, just as an amplitude. So I would like to go, because this is a pure sinusoidal signal, I would like to go to the RMS signal. RMS value that will be divided by the square root of 2, very simple in this case. So what we have is the following. I have this 25 volts peak divided by square root of 2. That's actually the value which I need to use to come up to the value of the capacitor voltage in RMS also. So that will be roughly 177 volts. That's RMS. Okay, if I now use this value in this equation, what do I get? I have the following. 1159 is equal to 177 squared divided by XC. So I know what X of C will be. That will be 177 squared divided by 1159. That's actually the value here. And if you do that and you round it off correctly, you will get 26.2 ohms. Okay, and since we know that the formula for the capacitor is 1 over omega C. Again, we are almost done, because if I rewrite this in terms of the omega and the XC, what I have here, this will be C is equal to 1 over the product of the omega and the C and XC, and the omega is given, which is 400. You can already see here. Let's move up a little bit. You can see it here because it's given. So I know that omega is 400, so I can move on, and I know the XC, so that is 26.2, which will be equal to 95.42 if you're a little bit more accurate microfarads. That's actually the situation for this example. Again, this example and example 2, we have used actually this figure to figure out what the required value of the QC was. In example 1, we just made this completely disappear, so make this theta actually 0. Then the situation was in that sense a little bit easier than this case. So we would like to have the power factor raised from some specific value to another value. If you want to raise it, you need to reduce your reactive power. To reduce your reactive power in an inductive load, you need to use a capacitor as a parallel combination and as a parallel configuration as shown here. And after that, you can calculate the required value of the capacitor. That's actually for this example. I hope this will clear out the situation. And again, keep in touch and share this video, and see you next time.